When you run machine learning at scale, the main challenge is usually not the model code. It is the data orchestration part. So let's look at the architecture of a production grade machine learning system. So it starts with the ingestion. We pull data from event streams, logs, and databases, and we can use Azure Event Hubs for live streams and Data Factory for batch loads. This data goes into a lakehouse, and here we clean the raw data and move it from bronze to silver tables, and finally the business-ready gold layer. Next, the features token act as our single source of truth. It ensures the model sees the same data during training and in production, which kills training serving bias. We use MLflow to track every experiment and version, so nothing gets lost. Once the model is in the registry, we deploy it, and after that we use a real-time or batch inference for the model serving. So we use real-time serving for instant answers, so batch inference for large-scale processing. Monitoring tracks model drift and model performance, and finally the output of the model can trigger business actions or automated workflows. In a machine learning system, we balance speed, cost, and complexity. So building this system requires making some technical trade-offs. I'll walk through a few examples. First is the choice between batch versus real time. Batch processing is cheaper and easier for historical data. However, for use cases like fraud detection, we need the low latency of a streaming architecture. Here we are trading system simplicity for data freshness. And second is the gap between offline and online features. It is easy to calculate features in bulk for training, but it is much harder to retrieve those same features in milliseconds during a real-time request. If these two versions don't match, we get training serving bias. So we have to decide if the performance gain is worth the extra infrastructure. Third is using a model versus heuristic rules. A complex neural network can easily find patterns that rules miss, but rules are easier to explain and more predictable. Many teams use both of them in a way that the model provides a score, and business rules act as guardrails. And finally, another one is latency versus cost. So using GPUs for inference is fast but expensive. For many companies, running models on a standard CPU is often better than using an expensive GPU. We trade a few seconds of speed for much better unit economics. So a good architecture must stay maintainable as our data grows. Every choice we make when we build the architecture affects our systems, time to recovery, and especially the cloud cost.